How do you do, dear students? Today we have the second lecture. The theme of this lecture, electric field, electric potential. At the end of this lecture, you will learn about electric field flux, Gauss theorem, electric potential, work done by an electric field, the relation between the electric field and the potential, and the notion of equipotential surfaces. To understand this lecture, you will need some vocabulary. They are electric field, электрическое поле или напряженность электрического поля. Electric field strength – это напряженность электрического поля, электр өрісінің кернеулігі. Бұл жерде здесь можно использовать либо электрический field, electric field, либо electric field strength. Оба выражения будут правильными. Potential of an electric field – потенциал электрического поля. Conservative field – консервативное поле, либо потенциальное поле. Dielectric permittivity of a medium – диэлектрическая проницаемость среды, ортаның диэлектрлік өтімділігі. Electric field – электр өрісінің кернеулігі. If to place a positive test charge at a certain point P of the electric field, then the test charge will experience a force, an electric force. The electric field at the point P is produced by the other charge Q capital. The ratio of the electric field force experienced by the test positive charge at the point P to the magnitude of this charge is called the electric field or the strength of the electric field at that point. So we see the electric field is equal to the ratio of the force that acts on the test positive charge to the magnitude of this test positive charge. Hence, the electric field at a certain point is equal to the electric force per unit positive charge. So we see that the electric field is a vector quantity and it is equal to the ratio of the force as a vector quantity to the test positive charge. The SI unit of the electric field is 1 Newton per Coulomb. If the electric field at a certain point is known, then the force experienced by a charge Q placed at that point is equal to the product of the charge to the electric field at this point. The electric field of a point charge. Every electric charge produces around itself electric field. So the magnitude of the electric field produced by a point electric charge Q at a distance r from this charge is equal to the ratio of this charge to 4 pi epsilon 0 epsilon r squared, where 1 over 4 pi epsilon 0 is equal to the electric constant, electric proportionality, which is equal to 9 times 10 to 9th power Newton meter squared Coulomb squared per Coulomb squared. The superposition of electric forces. At a given point P, each point charge produces its own electric field. So a test charge Q0 placed at point P experiences a force F1 equal to Q0 epsilon 1 and from charge Q1 a force F2 equal to the product of Q0 times E2 from the charge Q2, and so on. And the total force that the charge distribution exerts on the charge Q0 is the vector sum of these individual forces. So that is the total electric field, electric force, is equal to the vector sum of all forces acting on this charge Q0. This is the principle of superposition of forces. And the total electric field at point P is the vector sum of the electric fields at P due to each point charge in the charge distribution. So that is the total electric field at a certain point exerted produced by the charges in the charge distribution. It is equal to the sum of E1 plus E2 and so on. This is the principle of superposition of electric fields. The electric flux. The electric flux is a physical quantity that characterizes the amount of electric field lines passing through an imaginary surface. For a uniform electric field, the electric flux is determined as the scalar product of the electric field and the surface area. So that is the scalar product of the electric field and the surface area. So this scalar product is equal to the product of the magnitude of the electric field, the magnitude of the area, and the cosine of the angle between these two vectors. For a non-uniform electric field, the area is divided into many small elements, and the electric flux is calculated through each element, and the results are integrated to obtain the total flux. It is the total flux F is determined as the integral of the scalar product of elementary scalar product of the electric field and the elementary surfaces. So we take the integral over the whole surface. The SI unit of the electric flux is Weber. Gauss theorem. Gauss theorem is an alternative to Coulomb's law. It provides a different way to express the relationship between the electric charge and electric field. According to Gauss' law, the total electric flux through a closed surface is equal to the net charge Q, enclosed by this surface divided by the electric constant epsilon 0. So, according to the Gauss law, that is the total electric flux. The total electric flux is equal to the net charge enclosed by given surface and divided by the electric constant epsilon 0. Summary. Let us make summary of our lecture. So from this lecture, we learned that two physical quantities characterize the electric field. That is electric field strength and its potential phi. The electric field strength and the potential difference of an electric field are related by this expression. That is for the uniform electric field, and in a general form, the electric field is equal to the minus gradient of the electric potential. Moving with the direction of electric field means moving in the direction of decreasing of the potential phi. Field lines and equipotential surfaces are always mutually perpendicular. The lesson is over.